Hey folks, my name is Nathan Johnston, and in this video I want to show you a trick for evaluating certain sums that are really difficult to evaluate without this trick. Okay, so the example sum that we're going to use to motivate this trick is this one right here, where we're summing up a product of binomial coefficients. We do 2j, choose j, times 2n minus 2j, choose n minus j. And then we sum that up for all values of j from 0 up to n, where n is just some fixed given to us positive integer. Okay, and what we would like to do is we would like to take this sum and we would like to evaluate it explicitly. We'd like to come up with some sort of closed form expression for it that doesn't involve a summation. Now, there are a couple ways that we might try to do this, okay? One thing we might try is induction, right? We might try evaluating the sum for certain small values of n, then try to notice a pattern, and then do induction to prove that the pattern holds for all n. And certainly you can do that, okay? Certainly, if you try this for small values of n, you're probably going to guess what the pattern is very, very quickly. So you're probably going to guess the closed form solution very quickly. It turns out, though, the inductive step is actually surprisingly hard. So we're not going to do that. Another thing that you might try is you might doing a sort of combinatorial double counting argument. That often works for sums like this, okay? So what that might look like is you say, okay, well, I mean, binomial coefficients, those count the number of ways of choosing things. So I could sort of interpret this sum as I've got 2n objects, and I'm choosing j of 2j of them. And then I'm also choosing n minus j of the remaining 2n minus 2j of them. And then I'm doing something with those j and n minus j objects. Maybe I'm labeling them in some way or something like that. And then I try to count the number of ways of doing that exact same thing, but I count them in a different way. And that gives me a different formula for this sum here. Okay, and it turns out that there's kind of a way to do that combinatorial argument, but that's also really tricky. So we're not going to do that either. Instead, what we're going to do is we're going to use Taylor series actually to evaluate this sum, which maybe seems a little bit surprising at first. But this is a really common trick for evaluating sums where you've got sort of a sum of products and sort of the index in the products is running the opposite way. Okay, so for example, in this sum here, like the first thing that's being multiplied in the product, the 2j choose j, like as I sum over j, that j is increasing, okay? My first index is increasing, and then the second term in the product there, the 2n minus 2j choose n minus j, like there the summation index is decreasing, right? As j is increasing, n minus j is decreasing. And when you've got that sort of situation, that's when this trick is going to work. So let's see how it works. Okay, so let's start off by showing you how this trick that I'm going to introduce, how it works for this sum in particular, and then we'll talk about how it works generally after we work through this example here. So I claim that if I define a function f in this way, where I do a sum, I do a Taylor series sort of thing, where I've got a sum from n equals 0 up to infinity of x to the power n times coefficients that are just these binomial coefficients, 2n choose n, I claim if I define a function in that way, then that sum that I want up there, that ugly one where it's a product of binomial coefficients, okay, I've labeled it with that green star there, I claim that that sum is exactly the coefficient of xn in the Taylor series of f squared. Okay, and I'm going to try to convince you of that now, but like, why would that be useful? Like, why is that a good thing to know? And well, that's because, like, if I'm able to find a closed formula for this function f, which I'll be able to do, then I'll be able to find a closed formula for f squared. And then all I've got to do is I got to find, well, what are the coefficients in the Taylor series for that function f squared? And that'll just, boom, give me my answer. Okay, but let me try to convince you of this trick first. Let me try to convince you that this trick works. And well, here's how it works, okay? Let's just take that summation formula, okay, sum of 2n choose n times x to the power n all squared, okay? We're going to square that entire Taylor series now. Okay, if I expand that out, write it without summation notation just to help me get my head around it a little bit, then it looks something like that. And let's think about what would happen when I square this big, long, infinite sum here, okay? What we're going to do is we're going to focus on each power of x that we see after we square this out, okay? So let's start off with the constant term, right? Just the x to the power 0 term. How many of those am I going to see after I square this whole big mess out? Okay, and the only constant term that I'm going to see anywhere is from when I get the constant term of f itself times the constant term of f itself. In other words, 0 choose 0 times 0 choose 0. Okay, fine. Nothing too interesting yet. Let's go on to the next coefficients. Okay, what's the coefficient of x going to be instead? Okay, and this one's a little bit trickier. There are two ways when I square out this Taylor series, there are two ways that I might see an x. I might take the constant term of the first f of x times the x term of the second f of x, or I might do vice versa. I might do the x term of f of x times the constant term of the second f of x, right? So there are two ways I can get that sort of x term in the Taylor series. I might get 0 choose 0 times 2 choose 1, or I might get the other way around. I might also get 2 choose 1 times 0 choose 0. Okay, and so my coefficient of x in this big squared out Taylor series is, well, it's just the sum of those two individual products. Okay, let's go on to x squared. How am I going to see x squareds in the product when I multiply this out? Well, I might have an x to the power 0 times an x squared, or an x to the power 1 times an x to the power 1, or an x to the power 2 times an x to the power 0, right? There are three different ways that I can get an x squared when I square out this Taylor series. So I'm going to get a sum of three coefficients, right? I'm going to get the x to the power 0 coefficient times the x squared coefficient, plus the x coefficient times the x coefficient, plus the x squared times the x to the power 0 coefficient, right? I get three possibilities. And then I just keep on going in this way, right? For x cubed, well, there are four ways that I can get it, okay? X to the power 0 times x cubed, x to the power 1 times x squared, and so on, right? There are four possibilities, so I get a sum of four products, and so on down the line. And if I just squint really hard at these sums here, okay, at these sums that are the coefficients of different powers of x, well, throw it back into summation notation. That's exactly that green star sum that started this whole discussion. Okay, so fine and dandy, the trick works. Let's actually try to apply the trick in this particular case, though. Let's try to figure out what are these coefficients of x to the power n in this f squared series here. And to do that, well, the first thing we've got to do is we got to figure out what f is, okay? I already wrote down for you a Taylor series for f, but like if I want to write down f in closed form without an infinite sum, what's it look like then, okay? And I claim that f of x is just 1 divided by the square root of 1 minus 4x. I claim that's a nice closed form formula for f of x. And okay, in a sense, I'm pulling a rabbit out of a hat here. I haven't really shown you where that came from, but certainly, like, we can prove it, okay? Now that, we have a guess, we can prove it just by induction, okay? And what that would look like is you take that function and you just keep taking its derivative. And you could show by induction that the nth derivative of that function has this formula here. It's 2n factorial divided by n factorial divided by 1 minus 4x to the power of n plus a half. And I mean, that just comes from doing the quotient rule over and over and over again, or if you like, product plus chain rule over and over and over again. And every time, like, the function doesn't really get any more complicated, like that 2n factorial and the n factorial there, those are just constants, and it's sort of easy to keep track of how those change when you do derivatives of this function. You're just getting higher powers of that thing on the bottom, which, I don't know, as you get used to doing derivatives, that should seem fairly intuitive. Okay, so anyway, you prove that by induction, and then, like, the point of doing that is, well, Taylor series, like, they're defined in terms of the nth derivative of the function evaluated at x equals 0. So I'm just going to plug x equals 0 into that formula for the nth derivative, and I just get 2n factorial divided by n factorial when I do that. And then finally, I just plug into the formula for the Taylor series of a function, right? This is just a general formula for any function, how to construct its Taylor series. And I plop in that 2n factorial over n factorial for the nth derivative of the function at 0. And I get the coefficient in the Taylor series, like the coefficient of x to the power n, is 2n factorial divided by n factorial, and then divided by another n factorial. And wouldn't you know it, that's exactly 2n choose n. And that was the claim, right? Like, I wanted to show that f of x has exactly that Taylor series, and now I've done it, okay? So that f of x that, we defined way back in the day, yeah, it really does equal 1 divided by root 1 minus 4x. Okay, and now if I just carry this logic on, okay, great, I've got a formula for f. Well, I need a formula for f squared. And hey, that's really dirt easy, right? All I do is I take 1 divided by root 1 minus 4x and I square that, okay? So fx squared, that's got to be the function 1 divided by 1 minus 4x. Okay, and then the last piece of the puzzle is I need a Taylor series for that function. And remember, the claim was whatever the coefficient of x to the power n in the Taylor series of this function is, well, that's going to be what that ugly green star sum that we started with way back in the day, that's going to be what that sum equals. But this function here, 1 divided by 1 minus 4x, That's the function that you get when you add up a geometric series, right? This function here, this is just its Taylor series is the geometric series that has 4x plugged into it, right? It's the geometric series sum n equals 0 up to infinity of 4x to the power n. So the question is, what's the coefficient of x to the power n in that infinite sum? It's just 4 to the n. Okay, and that's the answer, that 4 to the n. That's the key thing that we've been looking for. Okay, so the upshot, once you stitch together all these pieces of logic, it's, well, that ugly sum of products of binomial coefficients that we started with, it's equal to 4 to the power n. And then we're done. We found the answer. Yay! Okay, so let's talk about this trick that we just did. Let's talk about it a little bit more generally, okay? How does this work in general? How can we apply it to other ugly summations of products? Okay, so this trick, it's called convolution, and in particular, it's called discrete convolution, okay? There are a couple different kinds of convolution. Sort of, I would say the more popular one is convolution of functions, right? Where you've got like a funny little integral and then a product of two functions. That's not what we're doing here. This is a discrete convolution. Okay, it's convolution of two sequences. Okay, in particular, the way it works is if you've got two sequences, okay, one of them's like A0, A1, A2, and so on. And then the other sequence, let's call it B's, okay, so B0, B1, B2. Then the convolution of those two sequences is the sequence whose terms are these weird ugly sums we just talked about. The terms in this new sequence are sums of products of the A's and B's, okay, where the A's have their subscripts sort of increasing and then the B's have their subscripts decreasing, running in the opposite order. And the way it works, the way that you can evaluate this sum here and find what this new sequence is, well, step one, find closed forms for the two Taylor series that have these original sequences, the A's and B's, as their coefficients. Okay, so you define f of x equals the sum of x to the power n times an, and you find a closed form for that. So this is like back in the previous example when we found 1 divided by square root of 1 minus 4x. That's my f of x. Okay, but then you also got to do it for the B's. And in the previous example, the B's were the same as the A's. So what I'm calling G here, that was the same as F in this previous example that we went through. Okay, so in the previous example, G was also 1 divided by root 1 minus 4x. Okay, once you do that, once you found sort of your functions that have these as coefficients in their Taylor series, next step, multiply these two functions together, right? Compute f of x times g of x, and that's going to give you a new function that has a new Taylor series. And let's just give a name to the coefficients of x to the power n in that Taylor series. Let's call them c sub n. Okay, and our goal is find a nice formula for c sub n, because hopefully that function f of x times g of x will be nice enough that we can reason about what its Taylor series looks like. Okay, and then we just sort of tie it all together. We conclude things at the end, and we just note that, well, wait, when I multiply f and g, the coefficient of x to the power n is exactly this weird sum that I wanted. It's this weird sum with j going from 0 to n of aj, b, n minus j. So that's got to equal cn, which I have a nice formula for. And then I'm just done. Okay, it's just, oh, well, if a function has this Taylor series and this Taylor series, boom, coefficients match, and boom, Bob's your uncle. It all works out. Okay, and yeah, this new sequence here, the sequence of CNs, this is called the convolution, the discrete convolution of the A's and the B's. Okay, so let's do another example. Let's just take that previous example that we had and tweak it a little bit, okay? So I'm going to do another sum of weird products, okay? It's going to be a sum from j equals 0 up to n of 2j choose j times 2n minus 2j choose n minus j, except this time I'm going to make it an alternating sum. I'm going to throw a minus 1 to the power j in front of the binomial coefficient. So now I'm sort of, adding the j equals 0 term, then subtracting the j equals 1 term, then adding the j equals 2 term, and so on, back and forth and back and forth. And the question is exactly the same as it was before. Can I find a nice closed form formula for this sum here? Okay, so this time I'm going to need a different function f from the function g, okay? It's not going to be I compute a function f and I square it, right? I don't do f times f this time. This time I'm going to do an f times a g, okay? And the reason for that is like sort of the piece that has just an index j looks different than the piece that has an index n minus j, right? Like the just j piece, that's this first piece that has minus 1 to the j times 2j choose j. Okay, and that's different from the second piece where the index is just n minus j, because there's no minus 1 to the n minus j on that second piece there. Okay, it's just the binomial coefficient. So they're different. So I'm going to have a different function f and g this time. Okay, but they're going to be very similar to each other, and I can get them from work that I already did earlier. Okay, so for example, okay, if I define an is minus 1 to the power n times 2n choose n, right? To sort of capture that first part of the sum there. And then I say, okay, f has got to be, the function that has that as its coefficient of x to the power n in its Taylor series. Okay, then what is that? Well, if I just notice that the x and the minus 1 have the same power on them, I can group those together into a minus x to the power n. And then I remember, like, if I had this, but it wasn't minus x to the power n, if it was just x to the power n, then that would have been my f from earlier. That would be 1 divided by root 1 minus 4x. Okay, so here I'm just taking that function and I'm plugging negative x into it. Okay, so it's just got to be 1 divided by root 1 plus 4x this time. Okay, just the sign of the x piece changes. And that's the only difference. That's what my function f is this time. All right, fine and dandy. And now I do the same thing for the second piece. To capture that 2n minus 2j, choose n minus j piece. Well, this time I'm going to say, okay, my second sequence in this convolution here, that's bn, it's just 2n choose n. Okay, so my function g, it's the sum of blah, blah. It's the function that has 2n choose n as its nth coefficient. And that, again, it's exactly 1 divided by root 1 minus 4x from earlier. Okay, it's that same function f that we saw earlier in the previous example. Okay, so that's step one. I found my f, I found my g, I found two functions that have the relevant sequences as coefficients in their Taylor series. Next up, step two, multiply them together. Multiply f and g together, and I mean, this is just a little bit of algebra. You're going to get 1 divided by root 1 minus 16x squared this time. Okay, and then the question that you ask yourself is, okay, well, what's a Taylor series for this function? Okay, and I mean, you can either start from scratch, start computing derivatives and stuff like that, and that's fine. Okay, but an easier way to go is leech off a Taylor series that you already know. And earlier, remember, we wrote down a Taylor series for 1 divided by root 1 minus 4x. It would be lovely if we could leech off of that one that we already know. And here's the trick. If you just plug 4x squared into that function, 1 divided by root 1 minus 4x, if you just replace the x by 4x squared, then you get this function here. You get f times g. Okay, so all I'm going to do is I'm going to take that Taylor series for 1 divided by root 1 minus 4x. I'm going to replace x by 4x squared everywhere. Okay, and then I'm going to sort of collect like terms and simplify a little bit. And what I'm going to get is my Taylor series is still going to have 2n choose n as its coefficient, but it's going to have an extra 4 to the power n from that 4x squared that gets plugged in. And now that's not the coefficient of xn anymore. It's the coefficient of x to the power 2n, right? Because, the 2 and the n multiply in the exponent there. And you only get even powers of n. Okay, so the coefficients in this Taylor series, the Taylor series for f times g, what's the coefficient of the odd powers of n? Well, they're all 0, right? There are no odd powers of n in this summation here, in this Taylor series. And then what's the coefficient of, the even powers of n? Okay, and it'll be a little bit careful here. Okay, I want to know what's the coefficient of x to the power n, not x to the power 2n. So I'm not copying down 2n choose n times 4 to the n. I'm copying down, well, replace n everywhere there by n over 2, right? Because I want the coefficient of x to the n. Okay, so anyway, the coefficient of x to the power n is 2n times n choose n over 2 if n is even. And again, it's 0 if n is odd. And then finally, just like before, we just stitch this all together and say, great, I found the coefficient of the Taylor series of this f times g. So that coefficient, it's got to equal this weird, ugly sum that I started with. Okay, so our conclusion is that this weird alternating sum of products of binomial coefficients, if n is odd, that sum is 0. And if n is even, then it's 2 to the power n times n choose n over 2. Okay, and maybe just as a bit of a, double checking our work, when n is odd, that sum equals 0. Well, that makes a heck of a lot of sense, actually, right? Because if you look at that sum, if n is odd, there are an even number of terms in that sum, right? J is going from 0 up to and including an odd number. So there's an even number of terms. Okay, and it turns out that they all just come neatly in plus minus pairs, right? The j equals 0 term is just the negative of the j equals n term. And then the j equals 1 term is the negative of the j equals n minus 1 term, and so on. So they all just perfectly cancel each other out, and yeah, you get a sum of 0. And we could have worked that out reasonably directly, but this formula for when n is even, that's a lot trickier to reason about without using this, Taylor series sort of approach here. All right, so that's the method, but before you go, I wanted to talk just a little bit about what got me thinking about this convolution trick recently. And it was, well, I was doing a research project, and in the middle of that research project, to make sort of a technical lemma work, we needed to evaluate this horrific double sum here. Okay, we've got a double sum. Okay, k is an index of the summation, j is another index of a summation, and then we've got sort of it's alternating in k, and then when we've got a four-term product of binomial coefficients. And in particular, we need to know that this double sum here was always non-negative. So we didn't necessarily, need an explicit closed form solution for it, but we at least needed to whittle it down to know that it's always non-negative. And because there's that -1 to the power k there, that's a little bit tricky. Okay. But sort of remarkably, like the tricks that we did exactly up here in this video, earlier in this video, they work on each of these sums. You can do convolution on this j sum, and if you do that, then it simplifies down like this. Okay, now we've only got one sum. We've still got that outer sum involving k, but the j sum has collapsed into a nice explicit formula. It's not quite enough yet because it's still alternating, right? I still don't know. Oh, that's definitely positive because like some of these terms, I'm subtracting them off. And how do I know that they don't win? Well, I just do the exact same trick again. Like this is another prime candidate for a convolution here because, I've got 2k choose k, 2n minus 2k choose n minus k. The summation indices are running in the opposite order. Actually, this is exactly the summation that we just went through, the alternating, sum of products of binomial coefficients. So you do that convolution again a second time now, and then you get this final closed form explicit formula for the original double sum involving products of four binomial coefficients. And then we just looked at that and said, oh yeah, by explicit formula, this thing is always non-negative. Yay, everything works out. Okay, so it's a really powerful trick that can help you solve even problems that look completely intractable on the surface. All right, and that's all I've got for you. Thanks for watching, everyone. I'll see you next time.